let's look at the two-dimensional vector v here. And it has two features, a direction and a magnitude. But if I were to ask you what is the direction of v, or what is the magnitude of v, you really have no way of describing that as I've drawn it here, just on a blank two-dimensional space. And so implied in any description of a vector is some coordinate system needs to exist behind it. So to actually describe this direction and magnitude, we need some underlying coordinate system. And we need it to basically span all of 2D space so that we can describe how big this vector is based on that system and what direction it aims in. I'm going to make a copy of this vector. And it doesn't matter if vector v is here or if vector v is here or anywhere else, because it is the same exact thing. It has the same direction, same magnitude, so it is the same vector. So I'm going to store these copies off to the side for a moment. And okay, to describe the direction and magnitude, I need a coordinate system. So I'm just going to draw an xy coordinate system for my vector v. So here I shall place a y-axis, and here I shall place an x-axis. And okay, now we're closer to being able to describe this vector because we can say, okay, it seems like it goes a little bit more in the x direction than it does in the y direction. But we still need something else, and we need to define a single unit of length in this coordinate system. So I need to say in this coordinate system, 1 unit in the x direction maybe corresponds to this, and 1 unit in the y direction perhaps corresponds to this. So I have to define my coordinate system with a set of axes and the size of a unit. And this kind of connects to the importance of a unit vector, because the unit vector essentially defines vectors that have a length of 1 in the direction of either axis. So I has a direction in the positive x-axis with a magnitude 1. J has a direction in the positive y-axis with magnitude 1. And now I can actually describe vector v based on this coordinate system. First, I can say, well, vector v, if I look at the eyes and I do another eye and another eye and another eye, perhaps we say that the direction of v, or the component of v in the horizontal x direction, has a magnitude of 5. So here's a vector that has a length of 5, and it's purely in the eye direction. It's 5 eyes. And then let's say let me pull this down a little bit. Let's say that the component in the vertical direction is a length of 1, 2, 3 j's. And so now we are actually able to describe vector v, and based on this coordinate system that we just defined, the vector v has components 5, 3. And so now you're like, okay, it has a length of 5 in the x direction, 3 in the y direction. Together, that would give a magnitude of square root of 34. And then the direction that v is actually going, this angle here would be given by tan inverse of 3 over 5 is equal to theta. And so now we can describe the two defining features of v, its magnitude and its direction. Okay, so that's great. We also could have defined our coordinate system completely differently. So here's another version of v, same exact vector, same magnitude, same direction, scroll up, confirm. But we could have built our coordinate system in a completely different direction. Perhaps we built our coordinate system like this. And so we define our axes to be like this. No reason we can't. We're defining this way to branch out and build this two-dimensional space. And so now we've got new directions for our axes, and we just need to figure out what our scale is. But our scale can be anything, right? I could make my scale such that this is 1 in the x direction. And I could do a matching scale in the y direction. This is 1. And then we can see that the vector v very clearly is given by component form of just 1, 0. In this coordinate system here, the vector v is completely in the x direction, not in the y direction at all, and its length is 1 unit in the x direction. And so it's pretty easy to calculate then that the magnitude of v is in fact 1, and that the angle of direction of v is 0 degrees. And so these two coordinate systems both work. There's nothing wrong with them. We could name this one like S, a standard coordinate system. We could name this one B, a different coordinate system. And then these coordinates 5, 3 might describe the vector v in this coordinate system S, or the vector v described in the coordinate system with a basis b, we would put like a little b saying its coordinates are 1, 0, and base b. And so we can build our coordinate system however we want. And to just further drive home this point, perhaps I build a different coordinate system, a third one, and maybe I'll just call this one E. And maybe I build it such that, I don't know, I could build it so that the y-axis is directly aligned with v. Or I could make it the negative y-axis. So I could put the positive y-axis here. I could put the positive x-axis through here. And then I could say, all right, well then my vector v is completely defined in the y direction, the negative y direction. And let's say that we make a unit in this thing. Let's say we make a unit that 1 is way out here, right? So if I were to continue this, this is the length of 1. So maybe v is actually at 1/2 compared to the unit vector. And the unit vector would really be this way. So if this is 1j, and we'll say 1I goes this way, then v is equal to negative 1/2 of a j and 0 i's. And so vector v in component form in this coordinate system would simply be 0, negative 1/2. And this is respect to our fancy E coordinate system. And then we could say, well, then the magnitude of v is just 1/2 of whatever units are defined in this way. And we can say that the angle of v in this coordinate system would be, you could say negative 90 degrees, you could say 270 degrees, either way. So our choice of coordinate system is completely up to us in two-dimensional space here. We can pick our whatever we feel makes sense. And usually the top of the paper might be positive y and the right might be positive x, but there's no reason we have to do it that way. And we're going to illustrate one more thing, and this is a little bit more advanced, but we don't even have to define a coordinate system at all with perpendicular axes. So if I start by saying I have a coordinate system, and let's just put x like this, I don't have to put y straight perpendicular to that. I could build some random y coordinate system where y is like this. And the idea behind this is I still might have a unit vector in the x direction. Let's call this one unit vector in the x direction. We'll call that 1i. And then we'll call the unit vector in the j direction, or the y direction, 1j. And so can I describe vector v based on this sort of askew coordinate system? And the answer is absolutely. Suppose we go 3 units in the I direction, so we go 3i, and then we're trying to get to v. So now let's say we have to go 1, 2 units in the j direction. And notice how j is not straight up and down. J is this direction. So I'm going this direction. And so perhaps in this coordinate system, I can describe v as being 3i plus 2j. And maybe we'll name this coordinate system W because it's kind of weird. So it seems a little weird to define a coordinate system without perpendicular lines, but we certainly can. And so That is a little less important, but I do want you to get the idea that we can at the very least define our coordinate system in any way we choose, as long as it spans all of 2D space. So as long as I can combine my two axes and cover all of two-dimensional space, we're fine. These three options are probably great for our purposes for class. This is a little bit advanced, but kind of good to see that we can actually do things like this too. One other thing I want to touch on here is if we look at, for example, the vector v here in this coordinate system, and we say that v is equal to 5i plus 3j. Okay, well, what does this really mean? We defined vector addition to be that if you take some vector here, which is 5i, and say you take some vector here, which is 3j, vector addition means that if we started here and we end here, well, then this is the vector that actually describes this is the vector that starts here and ends here, also known as vector v. So when looking at how these vectors work, you look for their start and their eventual end, and then you describe it as one vector. But I think something to notice here is this plus sign is like an operator here. And this operator actually combines these. And it morphs them into a single vector. And so it actually morphs them into v. So once you add 5i plus 3j, 5i and 3j are gone. Like, as soon as we actually add these are not here anymore. The result is this. So when to do 5 plus 3, the result is 8. It's not exactly the same because like the result is its own new vector. The operation produces this different vector. It's not like, oh, these two vectors are hanging out, and it's like, oh, you could walk this path, or you could walk this path. It's the sum of these is this path, which is a little bit weird because you kind of think it out like this, and you can break into the components to say, okay, it's equivalent to if you walked like this and walked like this, but their sum actually is this thing. And I'm seeing a little bit of students kind of not quite owning that idea. And it's a little bit weird and it's a little bit nuanced, but it's like the vector is this thing. The sum of these two things is this thing. And if you can play around with that and let that sort of, I don't know, marinate, maybe that can help a little bit with understanding how all this stuff works. So hopefully this was a little bit useful. Thank you for watching.